An interesting side effect of Faraday's law is the EMF induced in a linear conductor as it passes through a magnetic field. If we were to take a single straight conductor, like a wire, and move it through a magnetic field like this, it will generate an EMF. If you could connect the ends of the wire to a voltmeter as it moves like this, you would measure a voltage. Why? We think back to electromagnetism, and if we move a charged object within a magnetic field, there's a potential for magnetic force. So keeping this in mind and knowing that our wire has protons and electrons within its structure, we know that those protons and electrons would experience a force on them during this movement. So let's first consider the protons. They are, along with the wire, being moved to the right. So considering the positive movement to the right, that is the current, we point our thumb to the right. Our fingers for the direction of the magnetic field are pointing into the page, and this leaves our palm facing upwards. So the protons are experiencing a push towards the top of the wire. What about the electrons? Again, they're being pushed along with the wire to the right. So we would consider the current to be in the opposite direction, to the left. So let's point our thumb to the left. Our fingers for the direction of the magnetic field into the page again. And this leaves our palm facing downwards. So the electrons are experiencing a push towards the bottom of the wire. Now, we know that the pushes are happening and protons don't move very freely, but electrons do. So the electrons are all gathering towards the bottom of the wire, leaving a lack of electrons at the top. A positive charge at the top, a negative charge at the bottom, and we have an EMF. So basically, we've made a little battery by simply moving a wire through a magnetic field. So how would we determine the voltage of our new battery? Well, let's try and put something together. We think back to our electromagnetism equations, and we remember that we have an equation for the force on a charge that's moving through a magnetic field. F equals QVB, where Q is the charge of the object, V is the velocity of the object as it moves through that magnetic field, and B is the strength of the magnetic field. Now, we can use this to get the force applied to all those individual protons and electrons. But how do we relate this to voltage? Well, let's go back to our electrostatic section. Within the moving wire, we now have an electric field. Remember, it's positively charged on the top and negatively charged on the bottom. So within the wire, we have the electric field with the field lines going downwards. And we think, well, that would mean that there's a force on the electrons pushing them back into their default place. And it's countering that magnetic force. So we stop and think that, well, once the electrons have settled into the bottom of the wire, as close as they can get, they're in equilibrium. The magnetic force is pushing them to the end of the wire, and the electrostatic force is trying to keep them away from each other as much as it can. And so we can say the equilibrium is described as the magnetic force is now equal to the electrostatic force. And the magnetic force is our QVB, and from electrostatics, Fe can be replaced as QE, the electric field here. Now, the Q's are both the charge on the object, so they can cancel. And that leaves us with VB equals E. And we can relate this electric field to voltage using our electrostatic formula. E, the electric field, is the change in voltage over D. So let's swap out the D for an L, and that'll better represent this particular situation. Remember, the L is simply the length of our conductor, or the wire in this case. Rearranging, and we have voltage equals BL little v. And with an induced voltage like this, we commonly call it EMF, and we put our fancy EMF E symbol here. And here's our new formula for motional or wire EMF. That is the EMF induced by moving a straight conductor within a magnetic field.